So far, we've only looked at projectiles shot in the horizontal direction, and that's all well and good, but in real life, things get thrown in two directions all the time. We throw them up and sideways, or down and sideways. We rarely throw things just straight horizontally. For instance, here's a basketball shot. Let's just take a look and see what happens. Okay? You can see that ball moves to the right and up when he lets go of it. Okay? I'm going to watch that one more time, but this time I'm going to put in some points for every position the basketball goes through. So if we watch that again, okay, the blue dot that is left behind shows the basketball's position at each instant in time. Okay? Now this is not a position time graph. It shows me its x position and its y position at this instant, its x and y position at this instant. Okay? Now the motions are still independent of each other. It didn't change just because we are now going with an up and right motion. But we do have to be a little bit careful with our analysis now because our equations are going to work out a little bit differently because now there is an initial velocity in the y direction. There is an initial velocity in the x direction. So we're going to have to deal with that. Okay? Now what I have here is actually the first part of dealing with that. I've gone ahead and split the data out. This is just an exposition graph. Okay? So this shows me how the x position is changing at each instant in time. Now it looks like it's going up, but it's because it's moving to the right, right? So it started right here at time just past 0. It was just a half a meter in front of the origin. Okay? When we get all the way up to half a second into this thing, it's gone about 1.25 meters. 1 second into this thing, it's almost 3 meters away. Okay, 1.5 seconds, it's almost 4.25 meters away. Okay, now the slope of this line tells me its velocity. It's moving at a speed of 3 meters per second, 3.068 meters per second. And it is a really straight linear line. Okay, that's what we expect. There is no forces acting on it in the x direction. There are no forces acting on it in the x direction. So we don't expect it to accelerate. We expect a linear line. And if we actually go ahead and take a look at its velocity, this scatters a little bit less straight, but it still follows that 3 meter per second mark pretty close. Now, the variation is due to me when I'm clicking on where the ball is at, probably not due to the velocity of the ball changing very much. At these low speeds, air resistance really doesn't matter. Now, we're going to go to the y direction. Now, this is a y position graph, so this tells me how high it is at every instant in time. So you can see down here it started at about 2 meters high, 2.5 or so, and that's about right. If a guy's 2 meters high and he's tossing a ball up in 2.5 meters, now you'll notice it gets to a high point at about 6.7 seconds somewhere. It gets to its highest point and then it returns back to the ground. Okay, so it goes up, slows down, stops, changes direction, comes back down. Now I went ahead and did a curve fit to this. It's a quadratic curve fit. Okay, at squared plus bt plus c, and it gives me an a term for its motion. And remember that a term is half the acceleration. Now here's what I mean. Remember we have this position for y. Y equals 1/2 at squared plus v naught t plus y naught, where y naught's our starting position in the vertical direction, v naught is our initial velocity in the vertical direction, and a is the acceleration in the vertical direction. Now if we go back and look at the data it says our a term, okay, is negative 4.862. So I know I have the equation y equals negative 4.862 t squared plus the b term it gave us is 6.55 and the c term is 1.4. So plus 6.55 t plus 1.4 meters. So what's that showing is that this ball started around 1.4 meters high at time 0. At the beginning velocity of this thing was 6.55 meters per second, and it has an acceleration of, well, we don't have an acceleration. We have half an acceleration. Remember, negative 4.862 is equal to half a. So if I multiply by both sides by 2 to clear that fraction, I get 4 and 6 is 2 is 12 and 8 and 2 is 6, 7, 9.724 meters per second. Okay? So the acceleration according to this quadratic graph is 9.724 meters per second squared, which is what we expect, right? It's falling now. The only force acting on it in the y direction is gravity, so it is accelerating downwards at about negative 9.8 meters per second. But you'll notice we have this extra term in here. We have an initial velocity in the y direction, about 6.5 meters per second. So it was thrown pretty quickly. We also have an initial position, 1.4. Changing either of these things is going to mess with my final position. So it is important to notice that there are actually three things that this depends on. How fast it was going when it was thrown, where it started when it was thrown, and also the acceleration due to gravity. Those three factors affect how long my ball can remain in the air. Now I am going to take this one step further, right? I'm going to go ahead and look at the velocity graph and see what we see. So the velocity graph here shows me this nice linear fit. Now you'll notice the velocity has a constant slope of negative 9.736, like we just calculated, get the acceleration due to gravity. It does have an initial velocity of around 6.5, right? That is what we said, 6.5. And so that's our y-intercept, but it also crosses the x-axis, or in this case the time axis. Right around 0.6 seconds, 0.7 seconds, it crosses that axis. Well, why? Well, remember, this ball, let me pull up that video, goes up and comes back down. And when it gets to its highest point, right up here, it's no longer going up, it's no longer coming down, it stopped for a second. And that's what that shows us. It shows us that change in direction. So we have a velocity that is getting slower but still going up, and then getting faster but coming back down. During the whole time, the acceleration was constant, negative 9.8 meters per second per second. When the acceleration and the velocity were in the same direction, it got faster. When they were in opposite directions, it got slower, just like we expected. Okay? So just because we throw something up at an angle doesn't mean that the math has to get harder. It just means we have to deal with that initial velocity in the y direction.